Hello, it's me again, I'm Nafith. In this simple video, we're going to show you a bunch of configuration tasks that includes initial access, how to log into the switch, VRF and management stacking or dual control plane stacking, VSX, single and multi OSPF area, including external OSPF routes, how to integrate the solution with NAC server, ClearPass, port security.1x auth, as well as we're talking about the integration with the Aruba gateway to perform dynamic segmentation and what are the roles of local and downloadable user roles. Let's have a look. So the initial login to the switch to CX switches, username is admin, password is blank, and you can just select it. You'll be prompted for new password. You pick up your new password. You need to confirm it, and there we go. Now, it's a nice idea. Just create maybe base settings. There's nothing really on that switch. Show running config. There's nothing really. Very simple. There's nothing configured on that switch. That switch is a type of JL724A, which is a setting model 6200, and you can issue the command show module, I believe, and that will tell you what that switch is. It looks like it is 6224 different ports and 4 uplinks, SFP plus, which are 10 gig. So we can copy running config to checkpoint. Now again, we might call it factory settings or default. So we will configure the hostname config. You're on the config mode. Hostname will be, let us say, edge1. We will assign, and because this switch is going to be managed by the management port, which is outbound management, and in that there is interface, or let us say BRF built in, and that interface called MGMT. IP static, we will assign according to our network, and then default gateway. That's again, remember, this is management port. Now we need to copy this one into a checkpoint. Copy running config to checkpoint. Maybe we got lab 1 or something, or initial. Show checkpoint. You can see the checkpoint. You should see 2. The one we created initially and this one we just created. That's the latest one, and that's the user. Both of them are created by a user, and that's the time for these checkpoints. So we can look at show like HTTPS server. What's the state of that? It's on for default and MGMT interface by default, and the best access mode read and write. That's a default behavior. It means you can connect with HTTPS from either management or any interface that is a member of default VRF. And we can issue the same command, show SSH server. SSH allow us, so SSH server here enabled on the default VRF. So this is a behavior, or the behavior of 6200 VRF. HTTPS server is enabled on both default and MGMT VRF. And the SSH is only enabled on default. Right, and what we would like to do is look into a simulator switch or simulated switch and issue the command show HTTPS server. You can see that server is enabled only on MGMT, which is not the same as the behavior for the 6200, and show SSH server that is not enabled on VRF default by default. So it means you have to configure and enable SSH to be able to reach to that. enable that one on default, so we're going to exit this one. HTTPS server should be enabled on BRF default. And if you issue the command show HTTPS server, you're going to see that has now, compare this one to this one, it's enabled on both default and BRF, that is enabled management or MGMT. Now we can connect to the BRF SSH to that switch because we have enabled SSH server on the VRF MGMT, and you will be able to see that you are able to connect to that one. Remember, VRF is case sensitive. We're going to go to the config mode, VRF, we're going to call it keep alive. And then we will assign interface 9 to that VRF keep alive. And we will attach VRF attach keep alive. Remember, it is case sensitive. And then we'll assign an IP address to that specific interface after we assign keep alive to it. So 192.168, any IP can do, of course, because that's point-to-point connection. /31 is the best way. Remember, this is 8400 simulation switch, and we have this one layer 3 interfaces by default. So I can do show run current context, and we can see this is the config on the interface 9 that will be member, or that is a member of KA BRF. We're going to do something identical to this nearly, except the IP address will be different in core 2. So these are config BRF keep alive KA, and then we can exit here and to autocomplete interface 1/1/9, and then VRF attach keep alive, and we can see IP address in this case will be 192.168.0.1, and that is /31. And then show run current context, you can see, so probably show interface brief, we can see that interface 9 is admin down. That's a default behavior. Notice this is a default behavior. For that to work, of course, we need to bring the interface up. So we're going to go no shutdown, and at the same time we're going to do this one also, no shutdown, and we should be able to see that the interface show interface brief. See that interface is up. Okay, now we should be able to ping our neighbor. I normally start pinging myself, so 168.0.0 should be able, of course that's a VRF KA, and then we should be able to ping ourselves. We can ping the neighbor as well, and we can say repeat 1, yeah. Okay, so it's only 1, and that was able to communicate. So now we have established the communication for the purpose of keep alive. That's step number 1, and interface 9 is a member of that. I would like to assign an IP to VLAN 1, interface VLAN 1 for later usage. So I can go interface VLAN 1, and then IP address in this case will be 10.1.1.2/24, and we're going to do something similar to that one on the other switch as well. That will be 10.1.1.3 interface. So we can exit here if you like. That will enable the auto completion VLAN 1 with a space or without a space. So you can do this, and then IP address will be 10.1.1.3/24. What we would like to do is to create what's called a lag. Remember, the interface that is, or the interfaces between the switches will be 7 and 8, and these are, as best practice, we need to make them members of a link aggregation if we can. Now in this case we do have that capability, so we're going to go interface. Again, remember, if I am not in the right context, I can still issue this command, but it will not give me an auto completion. Show run current context, there's nothing on that interface. No shutdown. I'll make it layer 2, no routing, because that's a requirement, and VLAN trunk allowed all. and we're going to make its LACP mode active. So we're going to say show run current context. We can copy this, paste it on the other switch if you would like to, for ease of config, to make it faster, that's all. And I'm going to go exit in this case, and we'll just right click and show run current context, and that is now what we have configured on both of these switches. Now that's a lag 256, and we're going to make members of that lag 256. So in this case, I will so on this one we're going to go interface 1/1/7/1/1. It's like a range command, this one. No shutdown. Then we make a member of lag 256, and then that's it. And then we're going to do the same in this case. Interface again, remember 1/1/7. Again, it's like a range command /8. 1/1. I made a mistake. /8. Okay, let me exit. Interface 1/1/7-1/1/8. Now, no shutdown. It has to be done on the interfaces. Even if you don't shut down the lag, it will not push that no shutdown to the interfaces. And show run current context. You can see no shutdown, lag 26 for 7256, and for interface 8 is the same. What we can do, issue this command, show LACP interfaces. You can see everything is good and it's communicating, and both the state of the interface is up. And remember, this is LACP, so it would only be up if the other side is good as well. So I can issue the same command here, interfaces. You can see both of these switches, they have the lag interfaces up. We're going to verify connectivity. So in this case, we have assigned IP address to VLAN 1s, and we made this if you show interface trunk, you're going to see that lag is passing all VLANs with a native VLAN 1, which we have assigned an IP address in this case. So we can bring, if that works, say repetition 3, that works. It means the communication between on the lag 256 or 256 is working, and we are able now to bring the other side of the switch link. Now we're going to configure the VSX. So we start with core 1, and core 1 is going to be the primary, the role will be primary. So we're going to show VSX enter switch link. It's lag 256, the one we've done a few seconds ago, and the role in this case is primary. And we're gonna sync global. So settings that are global will synchronize automatically with the other member. As best practice, we're going to do system MAC as well. So we're going to manually specify the system MAC. It's an option, but it is highly recommended as best practice. And you can review the document for that. Show run current context. You can see system MAC. And we now, with the virtue of this, once we enable VSX on the core 2, that will pick up the system MAC dynamically because of the command VSX sync, VSX global. So here, what we're gonna do, the same, VSX, and we're gonna do enter switch link, lag 256, and we're gonna say role secondary, and that's it. We don't have to configure the system MAC. It should synchronize and pick up these settings from the other switch. We can see, we can view now and have a look to see whether that VSX is working or not. So VSX status, and we can see everything works. Notice the system MAC is being synchronized from the primary to the secondary here. Clearly is working. Of course, you can issue the command show run bsx if you would like. You can see what bsx details on this one, and I can issue the command bsx peer, so I can see the result of this command, but on the peer. That makes it easier rather than just need to console to the peer or to SSH. You can see all the configs on the peer as well, thanks to that command bsx peer. So what we need now is to reference the keep alive, the one we created with the vrfka, which is keep alive. So we are in the VSX context, and we're going to go keep alive peer. The peer for us is the 192.168, if you remember, .0.1, and the source will be 192.168.0.0. This is our source, and then VRF will be KA. And we will do something similar, but the other way around on the other switch. So we're going to go keep alive. We'll just copy this, VSX, and we're going to go, but we will swap this in core 2 because that's the IP and the neighbor will be 0. Yeah. And then show VSX brief. We can see keep alive established. You can see clearly keep alive established. It means we are protected against the stick or the splitting of the stack, or the brain split or stack split. We can issue the command show VSX status also, but I would like to see the keep alive. We can see everything works, keep alive established, all good and nice. And you can do the same and also issue this command with the VSX peer. So it shows you from the peer perspective in this case, and the role here secondary, the other one will be primary, as you can see. Yeah. And clearly, as we said before, show VSX status config sync, which we have enabled the global config sync, if you like, and we have you can clearly see it's operational, admin sys up, and simply speaking, there's basically it's up, and but there's no errors here also. There's no issues, so there are no recommendation for remediation because there are no issues. So in VSX, it's best practice to enable some global configuration for other features like AAA, BFD, BGP, VLANs, and so on and so forth. So it means whenever we create a VLAN here, for example, at this state, that will not be reflected on the VLAN as a new VLAN on core 2. So I would like to enable VSX synchronization for features of your selection. You can have, of course, the question mark. It shows you what features you can enable for the synchronization between different peers in that one. In that case, I would like to do AA or AAA, BFD global, BGP. I would like to do DHCP relay, so multi-chassis lag interfaces. If I would like to also do VSX sync with OSPF, quality of service, route map. So that makes life easy. So when you create something, when you do something, it will be immediately reflected for these features you have selected. Now, let us say we create VLAN, show run VSX sync. You can see what features we have enabled VSX to synchronize. Do you see this? So any of these features basically will be synchronized, and if I create a new user, for example, that would be reflected on the other switch. If I create a new VLAN, that will also will have a new user, BGP configuration, and so on. If you need to create a new VLAN, will that be synchronized or not? Let's have a look. So VLAN, let's say VLAN 11. or VLAN 12. Let's see here, show VLAN. Now that's VLAN 1 and 11. Here, show VLAN, show VLANs. That has not synchronized. This tells us VLAN is an individual feature or individual element that if you need to synchronize, it would not be under the category of global synchronization. So in this case, I can do VSS sync inside the VLAN itself. Now with that, I can now issue the command show VLAN. You notice that the new VLAN has been created in this case. So we can create other VLANs as well. And so we can say VLAN 12-13, that will create 2 VLANs, and we do VSS sync, and that immediately will add these VLANs to the other switch. You can clearly see. And that makes your life much easier when you do such a synchronization. Now let's create multi-chassis lags. So we go and we create multi-chassis lags. So we're going to go interface lag 1 multi-chassis. Okay, show run current context. You can clearly see this is multi-chassis, and immediately it has become access of VLAN 1 and LACP mode active. That is straight away. It is a multi-chassis. Now, if we check that on core 2, show LACP interface, you're going to see show interface brief. You can see continuing, and then what we're going to do, we will make this one a trunk, allow VLAN 1 11 to 13. So these are the 4 VLANs allowed. Description access 1. So, or edge 1 they call it. It's called edge 1. No shutdown. Show run current context. You can see all configs on that specific interface. Now, all what we have to do, because we have enabled synchronization of the multi-chassis lag, all what we have to do is to create the lag one on the core 2. So we're going to do interface we better get out of this, that's fine. Interface lag 1 multi-chassis. It will inherit all settings from the other switch. So if you show run current context, you can see all what we've done on core 1 has been pushed into this because of that global synchronization for the multi-chassis lag. Now we're going to assign interfaces. So we're going to go here and interface 1/1. This is the interface facing edge 1 switch. It's a member of lag 1, and we're going to do no shutdown in this case. And we will also look into the creation of the another multi-chassis lag interface goes to edge 2. So we're going to create that now. Interface lag 2 multi-chassis. Description edge 2. No shutdown. Now no routing, because that's by default is a layer 3, so we're going to make it layer 2, that interface. VLAN trunk native 1. VLAN trunk allowed VLANs 1 11 to 13. LACP mode active, even though you don't have to do this. And we go interface 1/1/2. Description is nice to give description to an interface, and no shutdown. Make a member of lag 2, which is multi-chassis lag, and we will exit. And the same story, we go to the other core switch, which is the secondary, and all what we have to do is to create interface lag 2 multi-chassis, and that will inherit all. I'm going to say no shutdown, and we're going to show run current context. You can see all settings that we have done in core 1, but we have to go to individual interface 1/1/2, and we're going to say description edge 2, no shutdown, lag 2, and that's it. What we need now, we created the multi-chassis lag on core 1 and core 2. We need to create the lags on edge 1 and edge 2, and then that will complete the settings. So we're going to create the lag interface on the edge 1 switch, and that's 255. Description link to the core, which are the two cores, no routing, and VLAN trunk allowed all, and no shut, and LACP, of course, mode active or even passive. And then we exit. We'll assign two interfaces to that, 23 and 24, and they will be members of that lag 255. So I'm going to say no shutdown, lag 255. Show LACP interface. You can see these are the two interfaces we're going to do. We should be up in both cases. Let's have a look. Now it's up. It was down on the core 2, so all that looks fine now. So VLAN, we create the VLANs, in this case VLANs 1, 11 to 13, and then interface lag 255. And then we're going to say description as best practice, no routing, VLAN trunk, allowed all, no shutdown, LACP mode active. And we should be able to see the but before that we need to map interfaces 23 and 24 and make them members of lag 255, and then no shutdown. And there we go, show LACP interfaces. We expect them to be up, all of them, unless we have an issue with the other side. Let's have a look. Coming up, 23 is down, and now it is up. You see, everything seems to be fine in this case, from access from edge 1, edge 2 to core 1 and core 2. If you would like to look at the neighbors, show LLDP neighbor info, you should be able to see we have neighbors on 23, local on 1.1, and neighbor on 7, 8, and 9, obviously. So that's very much expected, and you're going to see something similar to that one the other way around, obviously on the other side. Now on the VSX stack, core 1 and core 2, we're going to configure another lag that connects to the controller. Later on we're going to use that one for dynamic segmentation. So we're going to go for this. We can say interface lag 5, call it whatever you like to call it, and that's multi-chassis lag. Show run count context, we can see it's a multi-chassis. We're going to make a trunk, allow all, no shutdown, LACP mode active. And we'll make interface 5 as a member of that lag 5. That's the one connected to the controller, and we will no shutdown that one, and we will exit this one. And we'll do the same on the other core 2 interface lag 5, and if you remember, it's a multi-chassis lag, and this is show run count context. You can see it's a trunk now, but we need to no shutdown, and we go interface 1/1/5, no shutdown, member of lag 5, and we can say show LACP interface VSXP. That will be showing up on the other switch, so we can see that everything seems to be fine. And for itself, core 2 will be something similar. All LACP interfaces are up and running. And remember, the keyword or the key flag is MC. MC means multi-chassis. And on the controller, we can see show interface port channel 1, that is the connected one, and you can see it is connected interfaces 1 and 2, and they both are up. You can clearly see the protocol is up in this case. In this next step, we will configure the active gateway, which is virtualization of the default gateway for the clients in VLANs that are going to be serving the clients. So VLANs 11, probably some other VLANs as well. So we will go first go to core 1, and we will, because we already have VLANs 11 to 13, we're going to create interface VLAN 11, and we'll assign an IP address that will be 10.1, that will be 10.1.11.2/24, and then we're going to say PSX sync active gateway policies. So we're going to active gateway policies. So we're going to sync whatever policy we're going to create. So whatever you do here for the active gateway, it will automatically be synchronized to the other one. So what we are going to do, we will say active gateway, which is the virtual IP that will be configured as in the scope as a default gateway for the clients. And we're going to go with the MAC, just and that will automatically be synchronized to the other core 2 switch, which is the secondary. Active gateway IP. Yes, I forgot this IP keyword here. So we have that one. Show now. Show interface VLAN 11. We can see that active gateway has been configured with that virtual MAC and with that virtual IP. And now on core 2, what we need to do is simply just to create the interface for VLAN 11. So we're going to go interface VLAN 11. We have to assign a physical IP, as you would expect, .3 in this case, /24, and that's it. Layer 3 counters, so that will help us follow up with the communication. Count context, you can see now that active gateway has been pushed into that configuration straight away. Do some similar work to that for the VLAN 12 as well, and any other VLANs. We'll assign edge 1 the correct interface to VLAN 11 that is connected to interface 1/1/3, where the count is connected to VLAN access 11, no shutdown, and that should allow the client to pick up an IP with the correct default gateway, which is the active gateway. In this case, that will be 10.1.11.1. So that is our client IP config. You can see it has picked up a correct IP and with the correct default gateway, which is the active gateway. Okay, now on core 1, we're going to start the configuration steps for the OSPF. So first of all, we're going to create a single area. So start with the interface loopback. Loopback 0. IP address 10.1.0.2/24. That's the IP address. And then this is going to be used as a router ID. So we're going to create OSPF process 1, and the router ID is going to be the loopback interface 10.1.0.2. Show IP OSPF. We can see that it has, of course, nothing really, but it's a process 1, and then the router ID, that's the key thing that is enabled here, and the other parameters for that. We're going to create area 0 now, and then we can see show OSPF IP, show OSPF LSDP, the link state database. There's nothing, no OSPF LSAs, and we go interface loopback 0 and will enable OSPF on that interface, or IP OSPF 1 process ID, and then that is area 0. So we can review, because the area has been created now. Link state database, we can see link state ID is the only interface now that is being updating, if you like, which is the loopback interface 10.1.0.2. That is the link state ID, and the IP address of that, and link count is only one link that OSPF is enabled on. We'll go to core 2, which is our other switch. We're going to log in with the credentials, and we will need to go to the global config, VLAN 2. So continuing in core 1, create VLAN 2, and then that VLAN 2 VSX sync. It means that will be synchronized to other switch interface VLAN 2, and then IP address 10.1.2.2/31. We're gonna go now for of course core 2. We'll see VLAN 2 is enabled, is there basically, because being created by the virtue of VSX sync. But we need to create the interface for that VLAN, and we need to assign IP address 10.1.2.3/24, and we can ping. Actually, this is a wrong IP. Would like to make it /31. So /31. Probably we made the same mistake on the in here. I think that did not work. So /31. So we should be able to ping 10.1.2. We can ping ourselves, repeat twice, and we can ping the IP on core 2, which is .3, and that means the communication works. The link between the two switches is working. We would like to enable also OSPF on interface VLAN 2, if that is to be advertised. So now interface VLAN 2 show run current context. That's where we are in VLAN 2 interface, and we will enable OSPF 1 area 0, and we will also apply a cost to that interface, IP OSPF cost, that you can change, show run current context. It shows you all the configurations that are there. Now we should expect to have a more populated link state database. So show IP OSPF link state database. Give a few more seconds, and then it shows you what is being advertised. And for example, this is from core 2. We have here 10.1.12.3. That's on core 1. So we have two announcements on the actual core 1 and one announcement from core 2, and that has resulted into 3 entries, two from the core 1 and one from core 2. So here you can see clearly show IP OSPF interface brief. You can see we have two interfaces, one on VLAN 2 and one on VLAN on the loopback interface. You will notice something: the advertising router for that link is 10.1.12.3. The reason for this, because OSPF was created on core 2 due to the fact that we have the VSX synchronization, and we have enabled that VSX to also update OSPF. So if you have a look, show run VSX, you notice that we enable vsync. One of them will be OSPF. So whatever OSPF that was configured on core 1 was pushed into core 2. Now this is before we start the interface loop back 0 on core 2. And that's why it has picked up the highest IP address, and the core 2 highest IP address is the 10.1.12.3 that is deemed as the router ID. So on core 2 show run OSPF, you notice that is being created automatically, and this is due to the fact we have enabled global synchronization for that specific one. So let's create a loopback interface on core 2 and make that one the router ID, and we'll double check again the advertising router ID, in this case 10.1.0.3/32, and router OSPF1 router ID will be 10.1.0.3, which is the loopback interface, and we're going to say yes. And this means that we are going to see what is on that show run interface loopback 0. And we're going to see this is enabled, and this is because configuration is synchronized from core 1. Now on core 1 we should issue the command show IP OSPF links to the database. You're going to see a change in the behavior, meaning the router ID has been changed, and now this has been advertised as the router ID, and that also, now this is local one, okay, and this is the router ID advertised, that link on core 2. So remember the neighboring relationship is through the ISL link, that is a trunk port, and we have multiple VLANs. So show interface trunk. You're gonna see the link between these switches, and it's lag 256. It's passing all VLANs, and one of these VLANs is VLAN 2. So if I show the command show IP OSPF neighbor, that will be neighboring on VLAN 2, because that's the only show IP OSPF interfaces. Let's say brief. That's the only VLAN that's passing through with OSPF enabled. Obviously, the loopback interface is enabled, but it's not passing through that link. So the neighboring is based on VLAN 2. Notice it's full and it's BDR. So the neighbor is BDR, which is designated, the backup designated router, and that is a BDR. Now, the reason this is the default behavior of the interfaces in Ethernet, we can change that one to point. So we are going to change the neighboring show run current context VLAN 2, and we're going to say IP OSPF neighbor and network is point. Now show run interface VLAN 2, which is on our peer, and that has changed immediately to point. And we can say show IP OSPF neighbor, and I'm going to see different behavior. There's no DR and BDR, and the reason for this, now that interface is now OSPF interface, point-to-point interfaces. So we can show IP OSPF links to database. You can see 2 entries because that's not multi-access now. It's a point-to-point interface, and you can see advertiser routers, the IDs. These are loopback interfaces, and they will tell you how many links that they have to be advertised in this case. Let's have a look at the routing table. Show IP route OSPF. We can see that the loopback interface of the core 2 is visible here, and we can do the same on our VSX peer. We can see the other way around, so the local loopback on there, and our peer is seeing that. And of course I should be able to ping So from here, I can ping 10.1.0.3, which is a loop back on. I can verify that there's reachability from our loopback interface as well. So ping 10.1.0.3, we're gonna say source, we're gonna do loopback 0. We can type even the IP repetition, say 3. We are able to ping, and we have no issues with that. Again, remember, that's our neighbor, and it is on it's a point-to-point. Now, we'd like to also enable OSPF on VLAN 11. So we go interface VLAN 11 and IP OSPF 1, area 0, show run current context. You can see that we have enabled OSPF on that VLAN in this case. Remember, that has also enabled OSPF on our peer. Notice I issued this command, and that's on the peer, and you can see clearly this is great to have the VSX sync enabled. So now we should have the peering, 2 of them, one on VLAN 2 and one on VLAN 11. That's a link between the core 1 switch and core 2 switch. So IP you can see 2 of them. VLAN 2 is point-to-point, VLAN 11 is still broadcast multi-access network. So now we might want to make VLAN 11 passive interface. So we go interface VLAN 11 again, just to make sure. IP OSPF passive, and this show IP OSPF neighbor. That will stop the relationship because it's a passive interface. It doesn't send hello messages. It is reachable, but we cannot send hello messages. What we can also do, if you decide that all interfaces are passive by default, unless we change it, we can say router OSPF passive interface default, but I'm not gonna just issue this command. If you issue this command, simply speaking, all interfaces becomes passive. And this means if I issue the command show IP OSPF neighbor, you're gonna see no neighbors. So we need to make sure either just disable this command, or or you go to interface VLAN 2 and change it. Now that has changed, and it's gonna just take a bit of time to form a relationship. So we go now VLAN, again VLAN 11, IP OSPF passive. We would configure that as a passive interface. It should be interface VLAN 11, IP OSPF passive. We'll enable on the rest, so interface VLAN 1 and 12, IP OSPF area, OSPF 1 area 0. You can do 000 if you like, that's okay. And show IP OSPF interface brief. You can see a list of interfaces that are, of course, is gonna wait, and we will see that they're gonna come up soon. Now they are other on that loopback, point-to-point on VLAN 2 and BDR on VLAN 12. So multiple links between the two switches, i.e. multiple VLANs, and then each one of them will have the relationship on that specific VLAN. We can look at more details like the admin distance. So we can issue the command show IP OSPF routes. We can see the default, the cost relates to the bandwidth, and the distance is 110, which is default. Right. We can view the global routing table, show IP route. Now what do you see? You see O means OSPF update, so next hop to that destination to the loopback interface. The distance and metric and 110 and metric 1. Now metric is related to the bandwidth of the interface. C means connected, L means local, so C is connected, L local. What does this mean? It means when it says L local and C connected, the connected is simply speaking as a network where it belongs to. Example of this one, let's look at the VLAN 1. VLAN 1 local, which is the very specific physical IP address of that VLAN interface. And C connected is basically the network which that interface belongs to. So you can see each one of them has connected, and then metric and this of course 0 because these are all local. And the only one learned from OSPF is next hop, and that is the loopback interface of core 2. And we can issue the command the same for the VSX peer, and we're gonna see similar behavior, yeah, similar to this one. And again, remember that's on the other switch. Now we need to establish OSPF neighboring between the cores and the edge switches. So we're going to start by creating VLAN, two VLANs, 101 VSX sync. This would make sure that it's created in core 2. The same applies for VLAN 102. We'll go interface lag 1 and VLAN trunk allowed 101, and then interface lag 2, which is the link to the access to the edge 2, and VLAN trunk allowed 102. So simply we are allowing the relationship 101 and 102 between different core switches and edge switches. Now we need to assign an IP address to VLAN 101. There are 3 edge 1, IP address 10.1.101.2/24, IP OSPF area 0. We're going to do something similar on 102, and then edge 2, and then the IP address will be 101, 102 rather than 101, and then IP OSPF area 0. On the other VSX peer, which is core 2, you will notice VLAN 101, 102 were created automatically. We know this now. Interface VLAN 101, IP address 10.1.101.3, and then description layer 3 access to edge 1, and we're going to go interface VLAN 102, again IP address 10.1.102.3/24. Again, description. It's good to have description to the interface as good practice. Edge 2. You will notice show run current context IP address 102, interface VLAN 102, and interface VLAN 101, show run current context. Notice they have description and they have the IP address. Everything looks fine to me. In access 1 switch, we're going to configure VLAN 101. So VLAN 101 interface description layer 3 to the cores, and then IP address and that should have a good communication. It means you should be able to ping core 1 and core 2 switches. So we can ping 10.1 101.2 repeat 2, and that is also, and we can ping obviously .3 here, and we should be able to ping, that is the connection to the core 2 or the other member of the VSX stack. We would like to enable OSPF here, so router OSPF1 process 1 area. Let's say router ID, because we did 10.1.0.4 enable area 0 exit, we'll configure interface loopback 0, and we give it an IP address 10.1.0.4/32, and then IP OSPF1 area 0. So here we have enabled IP OSPF. We're going to enable that one also on VLAN 101, interface VLAN 101, IP there's an IP OSPF1 area 0, and exit. Show IP OSPF neighbor. There will be no neighbors because we have not yet enabled IP OSPF on the on core 01 or core 2 switches. So interface show run current context. There's no IP OSPF, so IP OSPF1 area 0. We can see that we have enabled that one, and if we look into VSX, show run interface VLAN 101 VSX peer. Notice that IP OSPF has been enabled, so immediately we'll go to edge 1 and we issue this neighbor command. You can see 2 pairs now. Clearly these 2 switches from the OSPF perspective, they are separate switches, layer 3 communication, and this is because that's on VLAN 101. One of them is DR, BDR, and the other one is DR other on VLAN 101. And if we go and just look into this, show IP OSPF neighbor, you can see it's DR on the edge 1 switch and BDR on the connection to the core 1 on VLAN 1. So different VLANs, different. Now we will configure multiple area or multi-area OSPF design, and we'll keep core 1 and core 2 in area 0, while edge 1 will be in area 1. So we're going to go, obviously that will be, the core 1, core 2 will be ABRs. So we need to make sure that they have interface in area 1 as well. So from core 1 perspective, we're going to create first of all area 1 OSPF 1. Area 1 is going to be created now. Show run current context. You see 2 areas now, 1 and 0, and we'll go to the interface VLAN. This is the one facing edge 1, IP OSPF 1, rather than area 0. We'll make it in area 1, and show run current context. You can see this is now moved from area 0 to area 1. Clearly that's the one. Now we will do the same or similar to that one. We'll double check again. We're going to make a change in core in axis 1 or in edge switch or edge 1 switch. We're going to configure area 1 on edge 1 switch. So go to OSPF 1 area 1. We say no area 0 first of all. Area 1 and interface VLAN 101 IP OSPF 1 area 1. So now that has become an area 1 rather than area 0. We're going to create like VLANs just for 128, 129, and we'll go interface 1/1/3 that's connected to endpoint, no shutdown, VLAN trunk, allowed 128,129, and then we will configure interfaces VLAN 128 and 129 to belong to OSPF area 1. So interface VLAN 128, we need to assign IP address first, 10.1.128.1/24, and then IP OSPF 1 area 1, that's that interface. We'll do something similar to interface 129, except the IP will be different, of course. And then we'll configure area 1, that is the one that now we'll just restart OSPF so we can update. OSPF 1. Show IP OSPF link state area 1. We're going to see updates that's coming from core 1. It's building, so we're getting more data now from different, so core 1 and core 2. Here you can clearly see these are the IP addresses of the core 1 and core 2. Again, what we're gonna do, we can see that what IP routes we receive now. Let's have a look. Show IP route. Always show IP OSPF route, the OSPF routing table itself. And it tells us which interface and what information to receive. We should expect something from 128 and 129. Then let's look at the global routing table, only OSPF entries. We can see updates coming from Edge 1 switch and advertising 128, 129. And this is the interface VLAN 1, the ID of course, this one, and update comes from the core 2 switch, and that is 10.1.0.3, which is the loopback interface on that specific switch. We'll assign Edge 2 to area 2 in this case also, so we create another area. For this to work, we need to create area 2 here also, IP OSPF 1 router OSPF 1 area 2 interface VLAN 102 IP OSPF 1 area 2, no IP OSPF passive. We're going to just remove, and we will then move to the other edge switch and enable IP OSPF on that one. We will create VLAN, we create a loopback and VLAN 102. That's the one that goes through it. Router 10.1.0.5, that is the loopback interface, and that belongs to area 2. Then VLAN 102, interface VLAN 102, IP address 10.1.102.5/24 IP OSPF 1 area 2. So this is now enabled on that interface. We will need to create also loopback interface. Create an area 2, and again the same, we're gonna apply also VLANs 128 and 129. Sorry, 192.193 interface 1/1/4. This is the one connects to endpoint, no shutdown, VLAN trunk allowed 192.193. Then interface VLAN 192, we need to assign IP. So IP address 10.1.192.1/24. Enable IP OSPF 1 area 2. Exit. Interface VLAN 193. Then IP address 10.1.193.1/24. That should have been 193, obviously. And then IP OSPF 1 area 2. Always mix up in the area 1. So we're going to restart. That will ensure anything relates to OSPF on core 1 and core 2 will be updated correctly, to kind of speeding up the process, if you like. Disable, then enable. Now we should see the neighbors now. Show IP OSPF neighbors. We should see the neighbors correctly configured, and that's through VLAN 102 in each one of them. So there are two separate devices, as you can clearly see. Core 1 and core 2 are separate. So in H2, we're going to call show IP OSPF routes. We can see the routing table that OSPF has knowledge about. And these, so the either is the inter-area routes that has been learned from different sources. And we're talking about these have been learned from 102.2 as well as 102.3. So basically, Edge 1 has updated 102.2 on core 1 and core 2, and they have updated our devices so you can reach them. And on core 1, we can clearly see that these routes should be in the routing table, OSPF. So they have learned these, and they have learned other ones as well. These are from Edge 1, and these two from Edge 2. We can clearly see them visible in this case. And we can also see the summary. So show IP OSPF links to the database summary routes in area 1. That is what has been filtered to core 1. And we can see the 192.1.9. These are learned also. So these are summary received on this one, and one of them will be 192 received from 10.1.102.02.3 as well, advertising router, so itself as well as the neighbor here. And you can, if you look at access or Edge 1 switch, issue the same command, summary area 1. We can see the summary as well, that who is the advertising routes. So this is basically a route sent to core 1, core 2, and they will advertise it to the rest of the network. Let's have a look also on core on this Edge 1. Show IP OSPF route to that destination 192. That is a route on Edge 2. You can clearly see this goes through 101.2 101.2 is the IP address of VLAN 101 on core 1, and that's the IP address of VLAN 101 on core 2, meaning to be able to reach the network that is advertised from edge 2, there's no direct relationship between edge 1 and edge 2. They go through core 1 and core 2. And you can clearly see that VSX from OSPF perspective, there are two separate switches and they have no two adjacencies because they are not seen as a single switch. As we always said, they are only single switch from the link aggregation perspective. We can summarize routes if need be. So on the core 1 switch, we can summarize what we advertise, OSPF 1, and we say area 1, range 10.1.128 /18, say, rather than 24, and type enter area. And you will see this is being synchronized on the show running as well on the core 2 OSPF VSX peer. You can see everyone has been summarized, and that's the configuration pushed into the other peer on that. And if you look into the summary, you will find this is being summarized by the /18. Now, means when edge 2 receives information about that network in area 1, it will be summarized that rather than the full route received from them. So previously we can see they received the /24. Now if you issue the command on edge 2 show IP, the same command show IP OSPF routes, you're going to see that this has changed from /24 into /18, and this is due to the fact that we have created a summary. Look at this. So 128, due to the fact that we have summarized these networks, and you can see they are received through two different neighbors, one through 102.2 and one through .102.3, which is basically core 1 and core 2, which are the members in VSX stack. We'll double check the interface on core 1 that connects to the router. That's interface 6. Show run interface 1/1/6. There's nothing in here, so what we're going to do, we need to configure that one with the proper address. No shutdown, IP address. Run count context. You can see this is what we wanted to look into this one. We should, from here, we should be able to ping, in this case, 10.255.101.11, repeat maybe 3 times. Now the ping works, so this is the connection, if you like, to the internet. We're going to create an IP route to a simulated, if you like, internet. So probably we can exit from here, then IP route 198.18.11.1. We're going to go to the whole network, .0 has to go through 10.255.101.11. Show IP route static. We can see we have created that. So we should be able to ping that destination now, 198.18.11.1. So that static route works as we could see it, and there's no issues whatsoever. We've also configured another static route, show IP route, so we can reach 10.2.5 networks. So that's also, that would enable us to reach the network 10.54.1 and this route. They both go through the router, and that's the IP address of that router. Now what we're going to do now, we're going to redistribute static routes into OSPF. And if you look into show IP OSPF links to database summary, we can see external routes that are configured. There's nothing in SSA or AS external route. This one, there's no external route, as you can see. There's no external route here. There's no external route here. There is no external route AS here. So basically, there is no external route. We would like to redistribute, so that's these routes will be link state type 5. We'll go to the router OSPF process number 1, and we're going to say the redistribute static, and we will issue the same command again, the previous command, and that will show us some external routes will be distributed. Let's have a look. And AS external C, 2 of them have been distributed. So that now we have external routes. To which destination? Show Area OSPF link state database external. You're going to see these are the link state IDs, i.e. these are the destination networks that we would like to reach. And they are reachable via router core 1 only. Obviously, probably we can configure also another static route on core 2 if we need redundancy, but at least for the time being we can reach that network through the core 1. Now in core 2 you can issue the command show IP OSPF link state database external. You should see routes advertised by the router ID, which is core 1. You're going to see something similar on edge 1, show IP OSPF link state database external. You're going to see these routes have been advertised by core 1, which has this router ID, and we can see there's a route to that 198.18.11, and we can verify this one, show IP route to that destination 198.18.11.0/24. There's a route to that, and it tells you it goes through VLAN 101, and then that is the next hop 101.2. And the same obviously applies to VLAN to edge 2, that will go through VLAN 102, and they should be able to ping that destination. You can see they can ping that destination, and the same should apply to edge 1, and we should be able to ping that destination as well. And this means that reachability to that external route is established through the links between the cores and the edges. We will, on access 2 or in edge 2, we will mimic an external route. We'll create a loopback, and then we create and redistribute that route into OSPF, and then edge 2 will advertise that route to other routers. So what we're going to do, we're going to create a static route here. So anything that reaches or arrives to that destination will be dropped basically. But that destination doesn't exist, so we're gonna just create a loopback interface. Now we'll call it 198 and IP address 198.18.14.1, and then we are going to redistribute this route into OSPF on that edge 2. So router OSPF1 redistribute static. We should see it now on other routers, obviously. So here on that core 1 now, we should see a route show IP OSPF OSPF routes to 198.18.14.0/24. That tells us it goes, it's an external route E2 type. Look at this, and that goes via 10.1102.5, which is the link to edge 2 in this case. And the same applies to edge 1, show IP OSPF route to that destination. You're going to see that has been learned via 101.2, 101.3, so Q1 and Q2, Q1 and Q2, and the type is E2. These are two paths or two routes to reach to that destination. If you trace route, you're going to see it goes through 101 and then goes to the destination, and that is simply speaking going through Q1 and then come down to H2. Now you can control that, and you can change the type or the type or the external type from E2, which is default, to external 1 to E1 if you would like to. We're gonna also create another null route here, IP route on Q1 to a different destination. And show IP OSPF link state external. So the external database, you can see now that has created another, because we already said redistribute static, so any route you create will be automatically redistributed, and that also will be E2. That will be E2, i.e. external 2. And you can see if you'd like to verify this one on any few edge switches, you can see that also there's a route to that. Show IP OSPF route to 198.18.11.0/24. That has been advertised by 102.2, which is the link to Q1. And obviously the same applies to .12, which we have just created. And that goes through these two routes, Q1 and Q2. So we're going to create a route map to change the type, the metric from E2 to E1. So we're going to define our prefix list first of all on Q1, and then we will we'll specify certain, which is the one route as E1. So we're going to say prefix list and router external, router A external, sequence 10, and what traffic we are looking at, 198.18.11.0/24. And then we're going to create a route map also. That route map, let's call it, this is just the name, whatever name, but you need to have a good name that will make sense to you, so intuitive name. And now we're going to reference the IP address and prefix router A external. There was a typo in the name of the prefix list, which I've changed it. Match IP address, prefix list, router A external. So show run current context. We can see that is the one that is matching. And what we're going to do now? So we matched it, but what we're going to do, we're going to set the metric type to external type 1. So whatever matches that one, which will change the metric type to, so anything from .198.18.11 will be matched, and then that will change the type from E2 to E1. And what we're gonna do, so we're gonna go to the OSPF, and we will apply redistribute static base on the root map OSPF from static. So now, if you go to edge 2 or edge 1 and issue the same command, you can see that the type has changed. Let's have a look. The type has changed from E2 to E1. Do you see this? And the other root has not been distributed because we only mapped on the distribution is based on that specific prefix list. So here we're talking about the .12 does not exist anymore. So if I go with the same here, that doesn't match, so there's no intro in this case. That's what it is. And we can also change the metric if you would like. And so the cost, we can change it if you would like to. Here is E1, and the initial cost is 125. So this is the cost that will be advertised to the edge. So the edge one is 125. Notice the previous cost was only 25 because that was E2. E2 did not calculate internal cost, but this has added the internal cost. What you can also control, you can control the cost that will be advertised by the router, if you like. So we go back to our root map, OSPF under from static permit sequence 10, which is going back and revisit this, and we're going to also add set metric to 1000. So show run current context. You can see we have made, or we've done two changes here. We set the metric and the E type, E1 or E2. So here we're going to see that this has changed from 125 to 1100. So advertised as 1000, then the internal cost was 100 based on the link speed, and that is now changed from 125 to 1100. Now we would configure stub area and not so stubby area. So we're going to go to area 1, which is edge 1, member of, and we will change that one to a stub area. So first of all, we're going to verify the default root. There's no default root configured here. Clearly, you can clearly see that. Now, we'll go to, because you're going to do this on the ABRs, so this means Co1, Co2, as well as you need to change the internal ones. So we go to Co1 switch, and we will configure everyone as a stub area. So show running config OSPF, also on VSX peer. You can see that everyone has become stub area. Do you see this? That's on the peer as well. So both of them now, without this one, of course, locally this area is stub. No. That has changed. Obviously, you need to change the same to all routers in area 1, which is edge 1 in this case. And we are going to see that because that edge 1 is an internal router. Again, remember, so if we show IP root, default root is not configured, and we have issues now because this is not a stub area, and we can see errors here, OSPF statistics on interface VLAN 101, because VLAN 101 is the one that communicate, and we have issues in this case. We have option mismatch. option mismatch, that will generate a mismatch from option mismatch. We have 23 buckets. Obviously, if you do it again, there will be more buckets option mismatch because these are the hellos. Now in this case, we must change this one, and we can clearly see that has lost its neighbors because show IP OSPF neighbor. There's no neighbor here because that's it. And clearly this is the reason. The reason is because we need to configure this one as a stub area as well. So router OSPF1 area 1 stub. Now that show IP OSPF neighbors now should see we will form a neighbor now. It takes a few seconds. We can see neighbors core 1 and core 2. Obviously now show IP root. You should see an entry because the default root injected due to the fact this area has been changed to a stub. And you can clearly see the type is enter area, and the metric is in here is 101. Now that has changed to stub, and you can clearly see that on this switch, double check if there's any route to external 198.18.11.0. You can see there's a next hop and there's a default route. So default route has been configured on that, or injected if you like, into that one. So we can say also here on that core 1 show IP route 0/0/0/0. You should not see any. The reason this is the ABR is the one that will inject default route inside the internal routers in that case. We can configure also, but remember this is a stub, but still we have summary routes from other networks. So I can issue the command show IP route OSPF. You're going to see a lot of entries, including the default route that was injected. Now what we can do, simply speaking, we can go to this core and we can say stub no summary. So basically router OSPF 1 area 1 stub no summary. So the result of this, we go to the edge 1 internal router and we issue this command. We're going to see all routes disappeared, the inter area, because these are all OSPF inter area, and they all disappeared. The only one that is left is the default route on this specific one. So that's clearly very clear. And if we issue the command show IP OSPF link state database sub external, we should not see any external routes at all. And this is a result of having configured this one as stub area. And if you'd like to see what is the summary of link state database, we're going to see 2 entries. These are the default route that were injected into, or was injected into this. Now still we can bring that destination because we have default route that will go through the core 1 or core 2. So just say 4, and you can see clearly. Now we can even trace route to that destination, 198.18.11.1. That tells us it goes through core 1 and then go to that destination. You can also bring to other destinations, so 10.1.0.5. You should be able, so you can clearly see how neat the routing table is now, and how we are able to reach to destinations due to the automatic injection of default route. Assume maybe a new route has become available, maybe local internet. Now we need to redistribute it into OSPF. That is not possible with the stub network or total stubby. Now we will create a dummy root, if you like, 198.18.13. So that will be null root. And we're going to create a loopback interface, or the loopback interface here, 198 IP address, that is 198.18.13.1/32 router OSPF1 redistribute static and exit. So that is basically not possible. And the reason for this, because we don't really allow that, because this is stub area. Show IP OSPF link state database, that should not appear in the link state database. You can clearly see there's no root, and and the reason for that is because it is a stub area. So I can do this one, even just verify external 0, absolutely nothing. The solution to this is to create what's called not so stubby area. So what we can do, area 1 not so stubby, and then show IP OSPF link state database. Things will be different now. It has been redistributed, plus the default root has been removed. So the injected one, due to the fact that this was a stub area, is gone. You can't just see it. So in this case, what we be able to do, we need to make sure that also the core one is also configured as not so stubby, because that's our ABR, area border router. So go here, OSPF 1, area 1, not so stubby area. So this means it will inject external roots, so we can clearly still see show IP OSPF neighbors, and we can see this one is a neighbor, yeah, so that's still a neighbor, that's correct. And actually this one, so let's have a look again, it is this one, .3 on VLAN 101, right? So VLAN 2, we said this is point to point, if you remember. So now we need to have a look in edge 2. If there's a root to 18.13, which is the null interface, the loopback show IP root. Oh, there's a comma here, yeah. This root injected on access to, and then in this case that has come through VLAN 102, and the next hop will be, in this case, core 2, and there's another one next hop which is equal cost multipath to core 1. So we're going to revert now. So we just proved and we discussed the stub area and not so stubby area. So we're going to just go back and revert the settings on core 1 as well as on access 1. So on edge 1, we need to check reachability of ClearPass, which is our authentication server. So we're going to go ping 10.254.123, just 2 repetitions. That works. I would like to create a DNS entry for that. So to use the fully qualified domain name, I'm going to call cppm.arubatraining.com map to 10.254.123. Should be able to ping cppm.arubatraining.com. That's pingable, and we get a response. It means reachability is established, and it is there basically. So we would like now to add the radius. So what we're going to do, so we're going to add ClearPass as a radius server, and that will be cppm dot arubatraining.com, and the key for this one plain text. I'm going to use Aruba123. That should establish the that's a command. I should establish the radius in here. So we have a radius server, and we're going to create a new group. There's a group called radius CPPM. So it's an option, but it's nice to have groups for different purposes. Radius CPPM. CPPM, just the name of the group we would like to create. And then we're going to add the radius server to that one. So we are inside the group context. Should run current context. There's nothing, yeah. But we're going to do server that is a member of that, cppm.arubatraining.com. That's the server. And we're going to exit. We enable accounting as well. So accounting, port access, start, stop, interim 5 minutes, and then group CPPM. So we have enabled that counting on that group as well. Now we would like also to enable dynamic authorization for the COA, and the command for this will be radius dyn authorization client. The client in this case is the ClearPass, so that is the one training.com. Hopefully I didn't make mistake in the name. And secret plain text Aruba 123 replay protection disabled. This is just to make sure that the time is not checked on the machine, on the message. And radius dynamic authorization enabled. So we said, where do we expect the dynamic authorization message to come from? The first command, and the next one we have enabled dynamic authorization. Again, remember, replay protection disabled is just not to check the time on the actual message that ClearPass, i.e. we tell the switch, don't check the time basically. Now, might be a good idea to create a username that will follow all the, to make sure the server is reachable. So we're going to say radius server tracking. So this tracking, there will be a username. That username is configured on the actual ClearPass. We're gonna check check that after we finish this. Password, plain text, Aruba123, and we will then enable that radius tracking. So radius server host cppm.arubatraining.com tracking enabled. So we're going to enable that tracking. So here, so we would like to enable interface 111. We go to interface 111, make it a member of VLAN 11, VLAN access. That's where the client is connected. Now we're going to say no shutdown. If everything works, if we go to the client and enable that interface, that should authenticate to the ClearPass and should pick up an IP address. Now we can see the client has picked up an IP address on that card. That's the card that is supposed to be connected to the switch. We can see also that on ClearPass itself. So first of all, we can see that the access tracker or the tracking username has worked and has been authenticated. Basically, it's nothing really in the sense that it's just to make sure that the server is reachable, ClearPass is reachable. We can verify the radius server details, so we can look into show radius. We can see that's the name and ports and all that stuff, and then we have the shared secret. Obviously, retries 1 time out 5 times. But they look healthy, and tracking is enabled. Tracking is enabled. here, and reachability status is reachable since that time. And you can look into also show radius server statistics. You can see authentication statistics, how many attempts and what are the answers for the tracking. Tracking request 8 times. Now we can see the responses 8 times. So from tracking perspective, this server is reachable and everything seems to be okay. So we will configure the AAA authentication now. Now that we're going to configure the authentication for the client connected port access .1x. This is .1x authentication, and that's the radius server group. In the server group we call the CPPM, if you remember. So the previous command looks like this. And then we will enable also the authenticator, i.e. AAA authentication. Again, port access .1x authenticator enable. So now this is enabling .1x, and the previous command was enable .1x radius group CPPM. Now we go interface VLAN interface 113. That's the one connecting to the client. VLAN access 1. And we'll enable the authentication of that interface. Authentication port access .1x authenticator. So authentication has been enabled on that interface by the enable command. So exit this one, show run current context. You can see VLAN 1 authentication has been enabled on that specific interface. We're going to go back to the machine and run the authentication on that card itself, meaning we'll attempt to do authentication. We have just enabled the .1x authentication on this one, and we're going to look into the authentication. We'll do some bits and pieces. Remember, this is a lab environment, so we're going to just perform a few things to make sure authentication works. Ideally, in the ideal world, you'd like to use certificate for that authentication, but we'll have a look, or we can push settings from the global policy objects that you can push if that is a member of a domain. So that's the card. We're going to right click, properties. We're going to see the new tab has been added, authentication tab. And in here, normally we would like to go settings, and we don't want to verify. Again, in real environment, you should not do that. And we go configure anything else. There's nothing here to do. Then we will go additional settings, specify the username. And this is, we'd like to use user authentication. The user authentication will gonna be used in this case. We give it a username, save credentials. So in here, we're gonna use ICX AVP1 and password Aruba123. So that's a username that will be sent to ClearPass from the switch. I'm gonna say OK. And if everything works, we will enable the card. Obviously now it seems to be not connected. So authentication is successful. You can see this, and if you look at the machine itself, you can find this has picked up an IP. So we can look at the status details that has been assigned an IP 10.1.11.51. So authentication is successful. Remember, we have also enabled accounting. So accounting is there. It will show you details still active, network details, utilization, and so on and so forth. Authorization session details. This is what we have achieved here. Now, if we need to verify the client that have been clients have been authenticated, show AAA authentication. That's on the switch, port access .1x authenticator, interface all, and client status will show me that we have authenticated client, right? And you can see that successful authentication is 1. There has been an attempt to authenticate initially, but that failed. Then it is successful authentication, and there we go. And that's on port number 3. On port number 3, the client connected to that is with that MAC address. Now we can look into show run interface 1/1/3. Notice that we have configured the VLAN on that interface as 1. But once authentication has taken place, you're going to see show port, show VLAN port 1/1/3. You're going to see the VLAN assigned 11. It's MAC based VLAN. Notice this is after authentication. If authentication stops, then the assigned VLAN will be 1. Go back to the default, the one we have configured. So basically that interface statically assigned VLAN 1. But then after the authentication, you'll notice that the interface has picked up or been assigned VLAN 11. We can look at the MAC address that is visible on VLAN 11. Show MAC address VLAN 11. We should see the MAC address of our device. We need to send some traffic, but basically now we can see that the client has that MAC address, yes, and let me see on the edge one, yes. Now look at this. Now port access security, we learned that MAC address of the client. Notice this is the MAC address of the client, 9E8A8. Notice 9E88, yeah. So that's the MAC address of the client connected to that edge switch. We can look into also the status. Show AAA accounting status. Interface old client status. We can see that session time. We know the session time and details of that specific one. Right. Now we can also in CX switches they will always assign a role. Whether that .1x or MAC authentication, they will assign an internal user role. They will always apply the authorization settings as a role internally. Now, if you apply your own role, that's different. But we just like to show you that these switches assign a role. So port access role, you're going to see that role has been automatically assigned to that specific user. And that role will be derived from the fact that's the role here. So this is an automatic role attribute authorization. Okay, it's doing nothing basically. It's just simply speaking, we have assigned VLAN 11. That's all. But the ClearPass says send back VLAN 11. That's what ClearPass has done to this authentication. But automatically will internally assign a role in here. You can also view the authenticated users, show AAA authentication, port access interface, all, client status, port access interface, all, client status. We're going to see the client, that's the MAC address of the client, and that is the username, and then authorization details, states applied. So the .1x authorization that has been applicable to that specific device. Right. If you again just review what the ClearPass is doing, what is sending back output, look at the output. This is the message that is sent back by ClearPass. So ClearPass will send the response. The response says the time on the system is 180 seconds, okay, 3 minutes. And it will send back a tile type 13, which is VLAN. And the private VLAN group ID is 11. That's the VLAN that is sent back. So instructions in the access accept message sent back to the switch to assign the client to VLAN 11. And that's where the VLAN 11 has been assigned. And remember, also we have the timeout 180. So the session on that, or the client session, will trigger and re-trigger authentication. Notice multiple authentication without having attempted, because there will be timeout every 180 seconds. Okay, so that's the time, and then look at this, 6:04 nearly 3 minutes, right? Okay, and after that, after 3 minutes, is going to attempt another one. We attempt to test change of authorization. So again, manually now, there's no condition to do it automatically. Right now, we're going to do change status, and I would like to send a termination request is a radius COA submit. That, if that works, that should send a request to disconnect. The client will reconnect again. Notice, successful for the client. This means we are enforcing the re-authentication of the client. Right now, we are enforcing the re-authentication of the client. There should be a new entry in the access tracker right now. So the client has attempted to connect now. And that attempt to connect, you can clearly see, has attempted again. And the client will have authenticated again, basically. I can verify that by show radius dynamic authorization. Now we can see that there has been a request and acknowledgement. One request, one acknowledgement. So these two showing to you. And then probably we can also look at that one from the client perspective. Any modification, show radius dynamic authorization client. Client IP, which is probably we can just have the client IP 10.1.11.51. The radius dynamic authorization client is not configured. It's okay. Oh, the client actually, sorry, client cppm dot arubatraining.com. That's the client. So there we go. And the user sessions modified one, which means disconnect and reconnect again. So we have sent a disconnect and reconnect again happens in this case. I would like also to further take this one step further to examine the role, basically. So we're going to create a class. We're going to create an IP-based class. We call it any, and simply just to make sure to demonstrate that concept, any from any source to any destination, any service. So that's the class, and then we will define a new class for servers as well. So client class IP, we give it a name, say servers. We're gonna match any to that destination 10.1.1.2/255.255.255.255. We do the same, another server, or pretend to be a server, .3. And we can have a look into that, show running config current context. We're going to see that's class, and we define two of them. We can remove second one, no 20, and then we go, you can see one entry in here. Okay, perfect. And we will create a policy. We're going to call it port access policy. We're going to come back after this. So port access policy, and we give it the name employee. So we can define the class, two classes, and we create a policy. And this policy we map to class IP any, the first class we created in this case. And so we can look at the actions, if you like, class IP any action. And we can look into what actions can be taken in this case. But we'll leave it at this point, and then we configure another policy we call contractor. And So we're going to exit this one, port access policy, name it contractor, and we're going to match class IP servers, yeah, action drop. So we're dropping anyone from here, and for class IP any will allow. So basically this guy or whoever contractor in that policy will not be allowed to reach servers. And we can show run current context. We can see that we have created a policy, another policy called contractor, that will not allow connection to the server's IP addresses basically. And the policy will allow administrators to perform to reach anywhere basically, or employees to reach anywhere. So we can see details of the policy contractor, show port access policy contractor. We can see we are dropping any packet that goes to servers, and we're allowing anything else, simply speaking. Now we're going to define a role. So here we're going to come out of policy, port access role employee, associate. So we're going to associate that with a policy called employee, i.e. these guys are allowed to go wherever they need. And we will put access VLAN access 11, meaning when that user connects and authenticates with that role sent from ClearPass, it will be assigned untagged VLAN 11 plus apply the policy that relates to the employee. We're going to create another port access role. So we're going to exit this one, port access role contractor. We'll associate this one with policy contractor. And we'll assign VLAN 11, access on VLAN 11, which is untagged. And then we'd like to show port access role, what we have configured. We can see we have done two of them. One of them is already in, that is the default given to the internal one, given to the authenticated user now. Contractor we created with the VLAN and the policy. Employee we created the VLAN and the policy, their own policies in each one of them. So that's great, and we are going to change the host name and to add VSA. So basically this is the reason we do this, because our ClearPass policies are mapped to this kind of, if you like, host name or part of the host name. Host name, so probably looks more elegant, just go host name. Again, I'm not going to change the name itself, but I'm going to change the extension VSA. I would rather do it like more elegant this way. We're going to test, we're going to change our username here. So we're going to go properties again. We're going to go authentication, additional settings, replace credentials. The username in this case is going to be ICX employee, ICX, and then password, in this case Aruba123. Hopefully that will have no issues, and it worked. Now, what has happened actually, if we go to ClearPass itself, you will notice a new entry here with another username called employee, and in that employee, in the output, we should send back a VSA called employee. So they have sent that employee back to the switch. So the user now will have been assigned an employee role in this case. And that employee role, simply speaking, is what dictates what policy is applicable to that user. So if you go here and probably issue the command show AAA authentication port access interface all client status, in here we can see the role that was assigned employee is no longer the default built-in role or the built-in role that was assigned to that user. Now show port access role. We can see contractor. Notice this is the command and that's the output. What do you notice different? We no longer have that internal role that was assigned before. This was assigned because the ClearPass itself did not send any role. But now because the ClearPass has sent a specific role employee, that is gone. Okay, so we have only this contractor manually created, and this is manually created and has been applied here. Again, we can test with a contractor role as well. So if we log in with a different username, then in this case we can go for this one and change the name from employee to contractor. So ICX, if that works, then we should get another role assigned to that user. It will be the same VLAN, but if you look at the switch now, you're going to see the role that was assigned. If you look into this command, you're going to see the role that was assigned contractor now. Yes? And that contractor will apply the policies. So basically in the contractor you can make sure that that policy has been applicable, and that is the one that we have used in this case. Let's try to make an inconsistency. We're going to log in with something that assign a role that doesn't exist. We might call it bad role or something. Okay, so we will go back to our PC and we'll log in with a different user that is invalid role, basically replace, and we're going to go ICX bad role, and we're going to see the status now, Aruba 123. Okay, and log in here. Now we're going to see the client status. Back to the switch, I'm going to see the client status. There's no role assigned, and this is invalid because the role that was sent back by ClearPass was not defined here. And if we look at to ClearPass itself, and this is the latest attempt, that's the user that we have attempted to use, and the output here is sending back something we don't have, a bad role name. So the VSA that was sent back, the role name does not or did not exist on the switch, and that's why that role has not been applicable. That role is not applicable or did not apply. Now we'll talk about the dynamic user role or downloadable user role that will push from ClearPass into the edge switch. So we're going to look into, first of all, we'll log in as employee, and probably we'll see what's the status of our communication, if that works or not. So number one, what we need to make sure is the time is synchronized between the device and as well as ClearPass as well as the switch. So we would like to make sure NTP is configured correctly. So double check the time on the switch, show NTP status. First of all, make sure the time matches. NTP is enabled, you can clearly see that. Now we need to make sure that because that is the downloadable user role will have to trust the relationship between the switch and the ClearPass has to be trust. And we're going to see the crypto PKI trust anchor profile. There's no trust anchor profile, we don't have one. We're going to create one now. So we're going to go crypto PKI TA profile. We're going to give it a name CPPM. This is a name. Now we're going to TA certificate. We're going to import certificate that is trusted root into this one. We're gonna copy, it says in here, paste the certificate in the PIM format and press Ctrl D. So after you paste the certificate, we're gonna have we're gonna copy the certificate from wherever we have it, and then we will paste it in this location. So this is the root CA that has signed ClearPass. We're gonna paste it in the trust anchor on the switch. We're gonna right click and then Ctrl D, and then we're gonna go Ctrl D. Do you want to accept the certificate? We're gonna say yes. So we press enter after you paste it, and then we're gonna press enter. We're gonna say Ctrl D, yes. So there we go, and we can see now show crypto trusted anchor profile PKI TA profile. We're gonna see one installed and it is valid. Notification check is not enabled for that specific one, but the actual TA certificate for the CA that has signed ClearPass is installed and valid. Now this has been configured. DUR admin. You only need a read-only administrator. Read-only administrator. It can be also a downloadable user role if you would like. Both of them will work. So read-only is enough to communicate and establish the trust relationship. We need to add that specific user into the switch. So the user is created as an admin user on the ClearPass. That has to be also identified in the switch. We can go exit. So there we go. So we have radius. There's the server, host, CPPM that already been defined. Aruba network, ArubaTraining.com, ClearPass, username, DUR admin, as we have seen that user, and ClearPass password will be plain text Aruba123 in this example. So probably it's a good idea to just check that we can ping cppm dot Aruba training just to verify .com. We are able to ping that destination, and we can see show run inside the running config. I'm going to filter that, include radius server. That tells us what's going on that with that radius server. Okay. Tracking and ClearPass username, DR admin, and the password we have created now. So it's being configured, and we can show radius server details. We can look into details of that radius server, and it tells you all what have been enabled on that radius server, and it tells you that the username is there, password, track the radius, reachability status, and so on and so forth. So we can see clearly everything is being configured correctly. Now we would like to have the CPPM user role definition. So inside the ClearPass itself, we're going to define, look at the profile for the user. So that's part of the enforcement. So we go ClearPass in the configuration, we go to enforcement, and the enforcement profile that we need to configure, and we just test what's going on here, and we can see this is the one that we're interested in. That's the role will be pushed back, and that, simply speaking, what we're going to be pushed back to the Aruba switch, and these are details of that role that will be downloaded into the switch once that role has been pushed. And there will be other roles, obviously, as you can see, one of them, but the rest are the same. Yeah, it depends who has the login and what kind of login, and so on and so forth. Of course, if you look at other ones, there might be some other things. So there are some different parameters for different roles that can be sent. So this is the attribute that will send a role, the name of that role, or the type of the role, the name Aruba CPPM role, and then depends on the condition, and that's the profile name, i.e. the action that would be taken, pushing back, and these are details of that specific role. We also changed the host name into the something to do with the role, the downloadable user role. So I'm going to change it to hostname edge1. And the reason we do this is because our policy depends on this kind of extension, host name or the NAT device name. Show run interface 1/1/3. That's where the connection, i.e. the authentication, is going to take place. We can see the authentication, and we have enabled authentication on that interface. Let's shut down the port to trigger authentication. So interface 1/1/3 shutdown, no shutdown. Let's see what the impact of that. Now we should see client has authenticated. Show AAA authentication, port access interface 1/1/3 client status. You're going to see the client now. We'll double check. The client is going to log in. So now it has authenticated, came up. Now we can see the role. That is the role that was downloaded from ClearPass, that has been pushed from ClearPass. Notice this is the role that was pushed from ClearPass itself. Notice that's the role that was pushed. And of course on the switch it will be given unique identification. If we look at the access tracker here, you're going to see the client or the user we have used, ICX employee, and the enforcement or the output here, it says push that role, okay, radius. So the role name is downloadable user role, the name of the role is this, and will be appended with certain values to uniquely identify that specific role on the switch to indicate it is downloaded. Now on the switch, if we check show port access role, notice that we have built-in role contractor we have configured, another built-in we have configured, downloadable that we have not configured on the switch itself. And notice that this role or the settings of the role can be also pushed, will be pushed into the switch, like one of the things that is VLAN 11, and it has this policy. And we can look into the role from ClearPass only. They will see this command will show you the role that was pushed from ClearPass, and we can see the policy here, basically show port access policy. Now we can see the policy that was pushed by that role itself. When you issue the command show class IP, it will let you know show class IP. They will tell you details of that specific one. So that's a class, and then whatever settings that has been included in that role, okay, has been pushed from ClearPass itself. Now we can try this for employee. So basically the user was employee, the user that logged in was employee. We can try different user that will push different DUR. So we're going to go and re-log in with a different user. So we're going to right click on this, properties, and we're going to use different user for, we'll replace the credentials. We're going to log in as a contractor. That has worked. Now you can clearly see. Let's look at the authentication status. Show. Let's just go out from this. We go show AAA authentication port access interface, which is the one we need is interface 3 client status. So we can see who has connected and who has authenticated. Now we can clearly see the client. This is the MAC address, that's the username of the client, and notice that's a different role has been pushed from ClearPass. Clearly that role is different than the previous role. And if I issue the command show port access role, you're going to see that role now is the one that we see along with the locally defined roles. The older one, the employee DUR, is gone because the condition is gone. And if I go with this ClearPass, so I'm just focusing on what ClearPass has told us, it's the contractor policy, and that's the role name that was pushed from ClearPass. If we double check ClearPass in here, we're going to notice that in ClearPass we have contractor here, and notice that what is being pushed here, output here, and that is the contractor role. Notice the exact role was pushed into the switch, and we can see clearly that it has. We will look at the policy. We can double check even the type of policy that was pushed. Port access policy, and notice what's this ambiguous command. Okay, fine. So policy. Notice a policy is there, and it is the type of the policy was applied in here is downloaded. Notice this, and that relates to what we have received from ClearPass. There are other policies for other purposes, but this policy was downloaded, and these are the classes inside the policy and what actions do these classes have basically. As per the configuration on ClearPass itself, they were pushed in there. So user-based tunneling, we'll look into how to integrate the ClearPass. Of course ClearPass would be part of it. How to tunnel to the mobility controller. We need to verify the licenses. We need AP and BIF license for that purpose. So show license. Here you can see AP and BIF license have been installed. So access point, and we have next generation policy enforcement. That's what you need in this case. And obviously you have to make sure that BIF is enabled, because when you install it, you will find that it has to be enabled. CDMM, okay, and we can see the BIF feature has been enabled, and that's all good and nice. Now we need to define the transport VLAN on the mobility controller that is going to be used as we call it transport VLAN, that will be carried in the tunnel between the switch and the gateway or mobility controller, and we're going to define that one at the level. We are there, so config T, and we're going to say VLAN 4000. Show config pending. We can see that, and we can write mem. That VLAN now exists on that controller. Show VLAN, and we can see VLAN 4000 has been added to that specific one. This makes sure that we can ping our mobility controller from our switch, otherwise nothing works. 10.1.1.6. So this is pingable. That's the IP address of the mobility controller, and as a good option is to configure the IP source interface for UBT, user-based tunneling, will be interface VLAN 1. So that's something we can do. Now we need to configure the zone. We will give that zone name MC, and then the controller IP will be the 10.1.1.6 as we have seen it. So the way we do it on the switch UBT zone, this name is just a name. It's good to keep it a meaningful name, and we would like to work on the default VRF. And the primary, we only have one controller, 10.1.1.6, and if we have multiple controllers or two of them, we will have to provide both of these. Enable that one, show UBT. We can see it's enabled, and the operation status is done. We have not yet established any tunnel with that UBT. Now what we need to do is the VLAN we defined, that transport VLAN, we have to make sure we configure this one also here. And now show UBT, you can see the VLAN has been configured. VLAN 4000, where is it? I missed one step. So VLAN 4000, you have to make it UBT client. So you have to define that UBT client VLAN as 4000, because otherwise it wouldn't know. It's just a normal VLAN. So show UBT now. The VLAN is showing now. VLAN identifier is showing here. So UBT status is up. The VLAN identifier, which is transport VLAN, is 4000. That's all sorted out and all looks fine and set to go. Let's have a look at the state. Show UBT state. And it says registered. Notice is ready for bootstrap operation, not only yet, but when it says registered, it means the communication between the gateway / controller and the switch is good, is established, but does not mean we have yet formed a tunnel. It does not mean we have yet formed a tunnel. Now, if we have the client communicated and authenticated, then the tunnel will have been formed. We'll have a look at that. Show tunneled. So probably we'll look into the controller. So the client, for as far as the tunneled client, as far as the controller is concerned, is the switch now. So there's a bootstrap, meaning like GRE heartbeat, if you like. Yeah, bootstrap or GRE. Show tunneled node MGR. Tunneled node. You can see that the switch is there, client if you like, that has formed that tunnel. Now we'll see the license usage here. Show license usage. So you can see one license AP, one PIF license. So the total consumption of licenses is 1, and you can see the data path tunnel. Show data path tunnel. We can see clearly that this is the one we have, and the source is the 10.1.1, and that's a switch IP. Is GRE tunnel, and details PSSID is the MAC address of the switch, and so on. Now we have a user role we have created already on the switch, and that is employee. We will go and revisit that and make that employee tunnel to the gateway or to the controller. We're going to just rename our switch to contain BSA, because our policy on ClearPass based on the switch has part of its name with a certain value, BSA. So we'll put this one back here, and our intention is to have VLAN 11 tunneled, so that VLAN 11 should be configured on the controller, and we must not have that VLAN 11 on the switch. So normally no VLAN 11. This is the one we would configure on the controller itself. And we're gonna go exit from here, and we go VLAN 11, and we would like to define a new user role on the controller itself. We can do this one GUI interface or command line. It's easier to do it from the command line because it's a simple one. MC employee. So this is, and this is what's called gateway role. Access list session allow all that exists anyway. This access list exists on the gateway, and we assign VLAN 11 for that role on the controller. Alright, so we've done all of that, and on the switch now we will revisit employee role. So remember, show port access role, we have already configured an employee. We'll revisit this one and make it tunneling to the controller. So we're going to go back, user role, port access. I mixed it up between it and the role employee. And here we're going to say go to gateway zone, the one zone name we created MC, and gateway role is the one we just created on the controller employee. Remember that, yeah? We're going to test it now, so we're going to now shut down the interface 113, shut down, then no shutdown. Let's test that login with the, I think it's employee, you're already done employee, let's have a look anyway. Show AAA. Show AAA authentication, port access interface 1/1/3 client status. We can see that the client is contractor. We're going to change that one to employee. So that's a locally forwarding traffic. We're going to go and just rename or re-login with a different username. Come here and then we're going to change, replace credentials with the ICX employee and password, whatever password. And that, if that works, a tunnel for that user. So it is, now look at this, it says enable. This tells us that we have different behavior sort of on the switch. We're going to see, okay, employee, .1x authentication, role employee assigned to that user, and it is applied. And we can go and see the UBT, so show user based tunnel. Who are the users who are tunneled in this case? We can see the gateway role that was communicated with the gateway is UMC employee. Of course, this is a simple one just to allow everything, but it will also show you that this is the tunneling is working. It says activated in here, and obviously we are able to see that this is absolutely fine. And we can look at show UBT state. It says registered everything, and remember when the first time when we looked at this command we could see this and that only. This part shows that the communication between the switch and the controller is successful, and this part shows you the VLAN was sent, the client has authenticated. Says user access anchor controller here, 10116, and that's the user, which is the client, the Windows machine, connected to interface 113, registered, bucket. The bucket is responsible to point to the controller. In this case, we only have one controller, and GRE key is 3, and we're going to see that key matches this key. And the UBT VLAN we have configured earlier is 4000. This GRE key, which means the tunnel identification, must match that tunnel on the actual mobility controller. So show tunneled, again this command, node manager mgr, user tunnel now, in this case user tunnel table. Notice the key for the tunnel is 3, so that matches the other one. And because the user role on this, we have configured the VLAN 11, the VLAN has overridden what has been sent by the switch back. We can look into the same command. We're going to see tunneled users command. We can see details of that tunnel user, so it tells you communicated 4000 overridden by VLAN 11. And the user is employee, ICX employee. Tunneled MAC address is the MAC address of the client. Tunneled node MAC address is MAC address of the switch, right? And then the user anchor controller, and that's 10116, which is this controller. And that's a tunnel. The key for GRE matches the GRE key on the switch as well. Things working perfectly fine with no issues whatsoever. Obviously, we can issue the command show data path tunnel. We can see that the data path tunnel, we have the GRE tunnels, and clearly you can clearly see that GRE is there and is being established. Now we can issue the simple command with no command on the controller, show user or user table, doesn't matter. We can see that the user, in this case, that's the IP address of the user, and the name of that user is ICX employee. Forward mode is tunnel, and the role, the gateway role that we have instructed the controller to assign is MC employee. The MAC address is the MAC address of that specific device, and default tunnel user profile here, and basically that's the IP address and then the interface through which it is connected. Again, we know ESSID, that's not wireless, it's wired, and that will be tunnel, and then BSSID, which normally the MAC address of the radio on that SSID, that is basically is the MAC address of the switch, and physically on the switch connected to interface 1/1/3. Okay, yeah, forward mode tunnel and so on. Right, perfect. We can see more details about the user, so we say show user with IP, which is 10.1.11.51. That's the user IP. We can see if there are any sessions, any flags, and any details of that user. There are no traffic leaving and coming to that user. That's why I don't see much here. And you can look into the GUI interface of the controller and see some more details. So we can go and look into the controller. So we come here, 10.1.1.6. That should take us to the controller interface. So we're going to log in and find out username, admin1, admin. Okay, look at the application details, so we can go to build a controller, and we can go to specific. So now there we go. If there are any traffic, we can look into this web network services. We can look at the host with the highest usage is only single host, simply speaking. Some destination also called multicast addresses and so on. We can go to the clients. How many clients? We have wide client, which is a single client, and we can connect to that client. Click on it. That will give me the client, if you like, details. We can see the client connected to that switch, and this switch is tunneled to this. Client is 1, which is the ICX employee. That is the switch, and that's the mobility controller where this is connected to. These are the interfaces, and there's some details about the controller, and that controller has one access. So this is just to prove. Of course, if we have more data, we would have seen more details of the clients that are connected, but now we only have one client, and the client is doing nothing basically.